Welcome to this lecture on the link between resource efficiency and climate change mitigation. Globally, mankind now extracts close to 100 billion tons per year of materials, construction materials, metal ores, fuels, and food materials. And these material flows are directly responsible for about half of total global greenhouse gas emissions and more than 90% of global biodiversity loss. On a per capita basis, we extract in high-income countries roughly 27 tons of materials per person in those people's supply chains, and this is about 13 times more than the level of material extractions in the supply chain of people in low-income countries. We need to manage our material flows and material extractions better in the future. And to understand how we can do this, we will zoom into the materials production that we use, in particular cement, plastics and steel production, because those materials and their production alone account for now 23% of global greenhouse gas emissions. So just supplying the materials that we need to build up our products and infrastructure, roughly 1/4 of global emissions. Those materials appear everywhere. 40% of those material-linked emissions appear in the construction sector. That is not a surprise, given that construction materials also by far are the largest group of materials, but also manufactured goods with other 40% are quite prominent. But all the other sectors also in some sense linked to material consumption. We need to understand how we can decouple the services that we enjoy from materials from their negative environmental impacts. And to reach that goal, a scientific understanding of those linkages, the G7 environmental ministers have tasked the UN Environment to make a prospective study on how material efficiency, the more efficient use of materials, can link and create co-benefits with climate change mitigation. This study was handed over to the International Resource Panel, and I was part of the modeling team, so we can now have some first-hand insight on how we, from an industrial ecology perspective, can model the material efficiency climate change mitigation link and what the results are for some major sectors. In incumbent energy system models, we often use aggregated demand modeling. So we have a driving variable, this is often GDP, and then we have a simple function with some parameters that translates the GDP directly into the resulting energy use for final services like transport and housing energy use. But of course, to have this chain in detail, you would have to study many more steps in the middle, and this is what we are doing in industrial ecology. We study the so-called service stock flow nexus. So we start with the notion of human well-being, for which we need services, shelter and mobility, and to provide those services we need in-use stocks, and to build up and maintain the in-use stocks we need both operational flows, for example the fuel to run your car, and we need the build-up flows, for example to expand the building stock. And those material and product flows are then linked to material and energy supply. So you can see there are at least 3 steps in between human well-being and material and energy supply. So if you have a function that directly translates GDP as a proxy for human well-being into material and energy supply or only energy demand, you lose a lot of detail that is needed to understand the decoupling options in greater detail. So we study the service stock flow nexus by using the energy service cascade. We start with a service demand. Every end-use sector provides a certain service. For example, passenger transport provides passenger kilometers, and residential buildings provide a cooled or heated living space to people. We then can split this service demand into different modes. In passenger transport, we have public transport, we have cars, we have walking, biking. In residential buildings, we have the different building categories, the single-family houses, multi-family houses, residential towers, and so on. And all these individual modes of service provision have their specific intensity of use. This is a parameter that describes how intensively the stocks are used, for example, how many people ride one vehicle on average. The stock items, the products, also have another parameter that's called the intensity of operation, for example, the vehicle kilometrage every year. So when you apply those 3 parameters, modal split, intensity of use, occupancy rate, or intensity of operation, the vehicle kilometrage, you can translate the service demand into a demand for product stocks that we need, the number of vehicles that we actually need that then are driven and transport people. Those product stocks are then linked to the material cycles: production, manufacturing, use, and recycling. And this is the stage where all the material efficiencies can enter. So we will, in our model, need to translate the product stocks into variables of the material cycles. And we do it with the following scheme. We take the future levels of product stocks needed to supply our services, which we have modeled with the energy service Cascade, to then apply a stock-driven model to translate the product stocks into the product flows that we need to build up and maintain those product stocks. And stocks and flows of products together can be translated into the material level by applying the material composition parameters of those products. And then we know how many materials we need every year to produce the products to then supply the services in the in-use stocks. We also have energy intensity parameters that translate the product stocks into operational variables and then the energy demand we need for their operation. And the overall system of the assessment that is presented here is shown here. So we have the material cycles from the mining stage, material production, fabrication, and the use phase, to then the reuse, remanufacturing, and waste management processes. And we have the energy supply system that supplies all the energy to operate these different processes, both the material related processes and the use phase where the products are operated. And the special feature of this particular MFA model here is that we can identify all the relevant material efficiency strategies and implement them in form of parameter changes. For example, we can have a parameter of the recovery yield. This is the parameter that tells us how much scrap we can extract from old products, and this parameter will change over time. We can also change the lifetime parameter of products over time to model a lifetime extension of products. We can improve the manufacturing yield, we can increase the share of reuse of products to the extent that is feasible, and so we can, by changing the parameters of this model over time, model a change of material efficiency, of more efficient material use in the entire system, not only in the waste management industries. The material efficiency strategies we have for individual products are quite diverse. Here we see the example for passenger vehicles, where we also, in addition to what I said previously, can change the material, for example, to imply lightweighting, and we can of course change the use pattern of passenger vehicles by improving the share of car sharing and ride sharing in the fleet. And the majority of the strategies shown here can actually be depicted in the model framework that we developed. And the same thing applies to the buildings, the residential buildings, where we also have reuse, lifetime extensions, and material substitution, for example, away from concrete to use more timber in wood construction where timber is available. We will, in our model, use detailed descriptions of future products to properly link service demand, product demand to material demand. So we have engineering models like FastSim for vehicles, or a building tool that creates the building energy balance based on climate to properly describe future buildings and future vehicles divided into different drive technologies, materials, and also different building types. So a very high detail bottom-up modeling of individual buildings and vehicles that can then be scaled up to the total following the results of the stock-driven model. So this is all the detail we put in here to not just go from aggregated GDP to aggregated energy demand in the different sectors, but we want to depict all the detail, all the vehicles, the materials, the individual drive technologies, because this is the detail that people talk about. We make policies not for translating GDP into energy, but for policies for individual vehicles, individual building types. So somehow we need to have them in our model to properly describe the policy effect. And the second reason is why we do all this detail, that every stage from vehicle use to vehicle production to material choice and so on represents an opportunity for decoupling. So we cannot just decouple energy use from GDP, but we can decouple at every single stage in the energy service cascade, and we can depict the policies there properly and investigate all the different decoupling options. The assessment we make is compatible to large-scale assessments that are running in different research groups, and for doing this we choose to make our scenarios compatible to the shared socioeconomic pathways and to the reference concentration pathways, SSP and RCP. That means we use established population scenarios. Wherever we can, we use established future service level, and where we cannot do that, we make our own assumptions that are compatible with the SSP storylines. We have results on the future energy system and its greenhouse gas intensity, so we can use that to make our scenarios compatible with ongoing assessments of climate change mitigation and adaptation in different socioeconomic conditions. The results that our model framework produces look like this. We have studied 2 sectors at the global level, but here results are shown for the EU. The 2 sectors are residential buildings, you see it on the left, and passenger vehicles, you see it on the right. And for each socioeconomic scenario, we have so-called reference emissions or baseline emissions, which are the red bars here. So if we introduce new products and change the energy system, emissions will change over time, and in 2050, after taking those measures, we will end at roughly 260 megatons for residential buildings and roughly 350 megatons for passenger vehicles. So these are emissions that include both the operation of buildings and vehicles, their energy supply, and the production of the vehicles and the materials in them. And now we can add material efficiency to the picture. We can change the yields in the processes, recycling and manufacturing. We can introduce reuse and longer use of vehicles. We can introduce material substitution light design, and we can introduce more intense use, for example by car sharing and ride sharing, or by reducing the floor space per capita gradually as urban patterns shift in the EU. And you see that all these strategies have a quantitative impact on the total emissions. Overall, on the building side, you can see we can have an additional emissions reduction of 25%, whereas on the passenger vehicle side, we can have additional emissions reduction of 40%. So these are quite substantial numbers that can be introduced by material efficiency that come on top of emissions reduction from more efficient products and from renewable energy supply. For the International Resource Panel report, we produce more professional graphics, but the message is essentially the same. Here you can see the study scope G7 countries and China and India as additional countries that are of large interest. And you can see that we can go from 2016 life cycle emissions down to 2050 by introducing more efficient products and changing the energy system. And at the G7 level, we have an additional 30% reduction potential of emissions in the car fleet by introducing the material efficiency I previously introduced. So we have additional reductions that are possible. That means material efficiency widens the spectrum of emissions mitigation strategies. For China and India, the picture looks different because there much more growth is expected to happen in the next decades. So emissions in the reference scenario will increase from 2016 to 2050, and then they can decrease again if material efficiency is implemented by roughly 35% of the then expected baseline for 2050. For buildings, both China and India and the G7 countries show a similar pattern. So we have emissions reduction in the baseline from 2016 to 2050 due to renewable energies and more efficient buildings. And then additionally, we can save 35% through material efficiency in the G7 countries and 60% in China and India, because the lock-in from existing buildings and car infrastructure is smaller in China and India than it is in the G7 countries. So we can focus on more material efficient or different buildings in the first place. Material efficiency can have a profound impact on the greenhouse gas emissions and the overall output of the material producing industry. This graph shows an example for Germany, where we show the emissions in the material supply chain, so material production and recycling, for operating the German passenger vehicle fleet. The default is roughly at 10 megatons per year, so this is all the steel and the plastics that need to be produced and recycled to continue producing Germany's car fleet and maintaining it. And those reductions will decline to maybe 7 megatons per year due to energy efficiency and fuel shift, and they can decline additionally down to 3 megatons per year if those different material efficiency wedges, as they're shown here, are actually implemented. So both the technical strategy, red and blue wedges through higher yields and reuse, can play a major role, but also the end-use demand wedges through car sharing and ride sharing. That would mean we reduce the overall throughput in the material cycles, we operate vehicles more efficiently to decouple service provision from throughput, and then of course also from material production and emissions. So the emissions reductions are possible, and in particular, as emissions reductions in the material production industries are difficult to do, so you would have to switch to hydrogen or use CCS, carbon capture and storage, this picture really shows an alternative way out, rebuilding the industrial system to focus less on material throughput and focus on more high quality products and their use in the use phase and use sectors. A similar finding holds for residential buildings, where currently 25 million tons per year are emitted to supply new buildings to the German building stock and to recycle materials from there. This can drop significantly to maybe 8 million tons, and if we in addition apply higher yields and especially more intense use, meaning gradually less living space per capita, those emissions can decline even more drastically, meaning that construction at some point can almost come to a halt because we have a very mature building stock already. This is of course a special feature for high income countries with a mature stock. Such a high impact reduction potential for more intense use is not possible in countries like India or other developing regions where the building stock has yet to be expanded. Overall, we see the following picture. We would like to place material efficiency in the spectrum of energy efficiency and energy supply. To do that, again for Germany, I made some counterfactual analysis. So we have here 3 socio-economic scenarios depicted: the LED, the low energy demand scenarios, and the basic SSP1 and SSP2 socio-economic scenarios, where SSP1 is a scenario with easy climate change adaptation and mitigation. SSP2 is more of a typical business as usual scenario with average difficulty of adapting and mitigating climate change. And then for each of the 3 scenarios we have this reddish gray bar on the left, which is a scenario that assumes no new climate policy from now on, no more efficient product, just continuing business as usual products and technology and energy supply as it is, only including future population growth or change and service level changes. And then from that reference case on, I switched on energy efficiency, so allowing more efficient products. That would lead to emissions mitigation in the green bar here. We also can transform the energy system to having more renewable energies, especially in the electricity sector. That would lead to emissions changes or savings corresponding to the blue bar here. And then comes material efficiency on top of that, which could additionally reduce between 1/3 and 40%. So these are the 3 red colors here. The supply side, material efficiency, that would mean better recycling and material yields in the manufacturing industries. Demand side, that would mean reuse and longer lifetime. And the sufficiency related strategies, that would mean more intense use of buildings and vehicles. So we can see that all these strategy groups are very important, and especially if you want to have deep emissions cuts like carbon neutrality and so on, it seems like that material efficiency is indispensable, especially since material production emissions are difficult to mitigate in the industry. Think of blast furnaces and cement kilns. From these results, we can draw a number of policy relevant conclusions, which I already reported, but also a number of scientific conclusions. The first set of conclusions here relates to the needs for system modeling in the future. And there, the major research need that we identified is a more consistent depiction of macroeconomics and the material cycles in future scenarios. So not only studying the future macroeconomic system and having materials as a small add-on in the end, and not only studying only material cycles without any macroeconomics as we did here in our study, but integrating it too, so that we have a economically and physically consistent future description of lifestyles that are sustainable. I think this is a major research need that we need. We also need better data related to materials. That means better information on product material compositions, better industry data on what is possible in the industry sector regarding reducing emissions and at which costs. We also need to link our service demand scenarios to lifestyle scenarios. Transport demand, housing demand, and also leisure demand are interlinked. And right now in our models, they are just open ends that need to be brought together on a good description of attractive, sustainable urban futures. This is very important to make the scenarios more consistent. At the policy side, we can conclude that material efficiency applies to all stages of the material cycles, not just to the waste management industries. And that means on the policy side, material efficiency needs to be encompassed much broader, needs to be captured much broader than just in the waste management sectors, including the use phase, including material production and manufacturing. Also, we in the future will have to have more interlinked policies that target at material use and climate change mitigation at the same time, for example, because we know the effects are strong, so we cannot just consider climate change mitigation or just consider employment without also having the link of the material cycles here considered. Whenever material-related policies are made, for example, industry support or technology support, the greenhouse gas dimension must be taken into account, must be assessed. This is very important to make policies that are synergistic on both the purpose that they're actually designed for and the material cycle and then energy use, climate emissions side. And in the end, we need to understand how policies may create barriers or remove barriers to material efficiency. The assessment I presented here is an open source assessment, meaning both the model framework we developed and the database, the inputs and result data, will be available for free or are already available for use in the broader community and for future improvement, which is needed to make those scenarios even more realistic and consistent in the future. And I want to close this lecture with giving this overview picture of what is needed in the future of scientific improvements to make this material efficiency climate change linkage assessment even more robust. Thank you.